Now if we have a density function, okay, remember we have our y equals x squared, our y equals 8 minus x squared curves represented badly in blue here. And we've got a density function. Now I've sketched level curves for this density function. Density function is densities 1 plus the square root of x squared plus y squared. Okay. Now how does that function behave in the plane? What is the square root of x squared plus y squared for point xy? What does that mean? Now people have a little trouble answering that, and that's something that really needs to become second nature to you. The square root of x squared plus y squared is the distance from the origin to the point xy. That's real important. Make sure you're really clear on that. Okay, so the density at any point is 1 plus the distance from the origin, 1 distance plus the distance at that point from the origin. Now what do the level curves of this function look like? Well, a level curve, you set this equal to some constant number, as long as the number is big enough to make the right hand side positive or non-zero, which it has to be because this can't be, I say positive, to make the right hand side greater than 0. Okay, we set this equal to some constant. If the constant is bigger than 1, then the square root of x squared plus y squared is going to be equal to some fixed number that's bigger than 0. Okay, so the square root of x squared plus y squared being distance from the origin, a level curve of this thing where this is set equal to constant for an appropriate value of c is going to be a circle. The distance is going to be constant. Distance from the origin is going to be constant. So level curves are going to be circles. Even more specifically, if the radius of the circle is, let's say, 8, that would be the circle through this highest point of the y equals 8 minus x squared curve, then 1 plus the square root of x squared plus y squared is going to be 1 plus the square root of 8. Because everywhere on this circle, the square root of x squared plus y squared has to equal 8. So that the density is 1 plus the square root of 8, which is about 3.7. Now the density at the origin, where x and y are 0, is 1. So that this, whatever this material is, it's 3 times as dense here as it is here. 3 times the mass per unit of area if you're here, 3.7 times the mass per unit of area if you're here compared to here. On a circle of radius 6, you're going to get 1 plus the square root of 6. That's about 3.5. On a circle of radius 4, you're going to get density of 3. Circle of radius 2, you're going to get a density of 2.14. I'm not sure I even saw that decimal when I looked at it, so you probably can't see it, but there it is. Okay, so we got this density that's increasing. It's increasing faster from here to here than it is from here to here, and faster from here to here than from here to here, and so forth. So the rate of increase of the density is decreasing. Still, it's getting denser as you move away from the origin. Now, what's that going to do to the mass within this region? Well, parts of the region out here are further from the origin than parts at this distance or at this distance. Okay, the closer you get to the origin, the less the density. And I'm talking about something I haven't yet talked about that I'm going to talk about. So forget that I even referred to this picture. I don't want to have to redo the video. Go back to our original region. Here's our region. Okay. We're going to do the same thing for this region, but after we talk a little bit about areas and polar coordinates. The strategy is very similar. Okay, well, to figure out the mass in this region here, we start by just considering a typical delta x by delta y rectangle. And we have to consider where it is, because the density depends on where we are. So where we are is, we're in a small rectangle that contains sample point x star y star. The x star y star tell us where this is within the region. And we're going to be able to use where it is to determine the density, because the density depends on where it is. Specifically, we're going to evaluate this density function at the point x star y star and assume that the density is the same throughout that small delta x by delta y rectangle. that's going to give us the mass within this rectangle. The mass within the rectangle is just density times area. The density is just the density at our sample point, delta of x star y star. And that's going to equal, well, that's our density. We multiply that by the area, delta x times delta y. Okay? So, and here's the rhetorical question, where in the delta x, delta y region are we? We're surrounding the point x star, y star, so we're not going to be far off if we assume that the density at this point, which is this, is the same throughout the region. We'll get this mass. And then as we take the limits, all the little discrepancies and uncertainties disappear, and we get the mass. When we do that, by analogy with integrals that we did in the preceding few videos, this region is described by x going from -2 to 2, so we integrate from -2 to 2 with respect to x, and then we integrate from x squared to 8 minus x squared with respect to y. But what is it we integrate? We integrate the mass contributions. The mass contributions are going to be 1 plus the square root of x squared plus y squared times your dy dx. So we perform this integral, we get the total mass. Now we're going to look at polar coordinates, look at areas in polar coordinates, and set up an integral, ultimately set up an integral for the same density function but in polar coordinates. And in a different region, in this region here. This region is easily described in polar coordinates. This region would be much more difficult to describe in polar coordinates. It could be done, but you'd end up with really nasty expressions.